Hello, everyone. My name is Zakarya Kabbara. I'm a PhD student at the University of Antwerp with AIVC Research Group. And today I'm excited to share with you some insights about the simulation-based design of smart centralized ventilation system that we were able to develop over the Flux 50 project towards smart ventilation. What I mean by centralized ventilation system is depicted on the picture. On the right with central air handling unit connected to ductwork system, and this ductwork system convey air to rooms or ventilation zones in order to circulate air inside the building. And I just added a subtitle here, just to brief you from the beginning of our main aim of this simulation-based design. It's to ease the design engineers' challenges and generate optimized designs. So let's get to it. Let's see what are these challenges and how are we going to ease these challenges and generate optimized designs using our simulation-based design method that we developed. So to start with the design challenges of air distribution systems or ventilation systems, when designing these systems, the design engineers are challenged to achieve a long list of variable indicators. This indicator indicates how good or how bad the system is. And the first indicator is the cost efficiency, and that's demanded by every design engineer's client or building owner. They would also demand energy efficiency, and that's not only their demand, but it's the demand of our climate ambitions toward decreasing the energy usage. As you may know, buildings are responsible for 40% of energy usage, and the ventilation systems has a good share in this 40%. Studies have also shown that we as human beings spend around 90% of our times indoors. And that brings me to my next three indicators, which are acoustical comfort, hygrothermal comfort, and healthy indoor air quality. As we spend our majority of our times indoors, it becomes crucial to achieve indoor comfort and healthy indoor air quality, and that's for our productivity sorry, and well-being. Another indicator is having an aesthetic system. As you may know, the HVAC design comes after the deciding on the building architecture. And this poses some challenges on the design engineers because they have to deal with deciding on the routing of the ductwork system or the layout and the sizes within this architectural limitations. And that's actually additional layer of challenge when designing air distribution system. And the list can carry on, but what I would like to say here that all of these indicators has to be achieved by the design engineer within minimum budget and time. And by now you can put into perspective how challenging the design of centralized air distribution system is. So what we wanted to do in this project is to find the cure for these challenges. And by that, I mean the simulation-based design method that we developed for informed decision-making to help the design engineer in the design process. So let's see what's the aim of this simulation-based design method. So here is the deal. For a random floor plan, such as the one you can see here, we can give the position of the fan and the positioning of the air opening, and we want to determine the duct automatically using our simulation-based method. So that's main aim, and we want to generate optimized ductwork configuration, and that's include the ductwork layout and sizes. So the automatic generation of optimized ductwork configuration, that's our main aim. And the optimization objective here is to minimize the life cycle cost, and that includes the ductwork material and installation cost and the fan energy cost. By looking at the fan energy cost and keeping in mind that we are dealing with smart ventilation system, which means that we are dealing with variable occupancy behavior and partial load behavior, that means that the fan will be operating at partial load behavior as well. And that brings me to my first input that I would like to mention. Not only will we include the nominal flow rates, such as what the conventional design method do, but we will also include the demand flow profiles, because we are dealing with smart ventilation system and they have variable occupancy or variable load profile. So in this project, we realized that the ventilation system will operate the majority of the time at a partial load behavior. That's why we wanted to include the demand profiles in our input. How does these demand profiles look like? Let's have a look at a room, and let's say this is an office room, and people starts to come at 8 a.m. in the morning, so you can see the flow demand increase, and then they leave to their lunch break at 12, and then the demand decrease, demand flow, then they come back, increase again, and then they leave to their homes, and then it decrease again. And that's pretty much how in a very simplified way, how the demand profile works for one room, and we will apply this for every single ventilation zone in the building. The second input I would like to talk about is the location of air openings. So the location, we assume here that the location of the air openings to be known. We recognize that that the location of air opening can impact the ventilation effectiveness. Can impact the ventilation effectiveness and the ventilation mix in the ventilation zone, as you can see in the CFD simulations here. So an in parallel research was running at TU Eindhoven to realize the optimal position of the air opening for the most effective ventilation. That was in parallel. Long story short, they were using CFD simulations, but the normal CFD was apparently has high computational time. So they find out that the simplified CFD simulations can be promising. However, further research was needed. But what I want you to know here that we assume that the location of the air openings to be known in advance. Okay. After the design inputs, we also feed the design method, the simulation-based method, with boundary conditions as well. And these include hard boundary condition and soft boundary conditions. What I mean by hard boundary conditions, that means that the design has to achieve these conditions no matter what. Otherwise, if the design was not able to achieve these conditions, the design will be considered unfeasible. Okay, so the first hard boundary condition is the maximum velocity, and that can be determined using the local standard. For example, the velocity in shafts the maximum velocity in shafts is higher than the duct velocity in rooms. The second boundary condition is the maximum duct dimensions, and that's to deal with the architectural limitations that we have in the system. We have one soft boundary condition, which is the pressure balancing. And to help me explain the pressure balancing, let's have a look at this example in the figure here. So we have a fan and duct system with two branches. The design of this system is not balanced, and that's because there is an overflow in this duct branch, and there is the shortage of flow in the other branch. And okay, let's say this is the design that we have. Okay, it's unbalanced. If we rely on this design, that means that when commissioning or controlling this system, we will highly rely on pressure valves or dampers. The high reliance on pressure valves will pose some noise radiation from these valves and some acoustical issues. It may also have some control issues in the future as well. So in order to have a pressure balanced design, we should change the dimension of the duct system to better meet this the pressure balancing, and we have therefore less reliance on the damper. So let's have a look here. So if we decrease the size here, we will have less reliance on the sound damper, and hopefully will not have the acoustical issues and the control issues that may be imposed in the future. So that's it. So we applied the method on a real test case, which is the University of Antwerp, the floor of the University of Antwerp, and we compared the method that on this floor plan. We know the fan position, the air opening position. We compared our outputs with the existing system. So the existing system looks like the system on the left, and the optimized system with optimized layout and sizes looks like the system on the right. And the results that we were able to achieve, we had 18.5% reduction in the material and installation cost, and 10% reduction in the fan energy cost, and that comes to a total of 15% reduction in life cycle cost. But not only this, we were able to also achieve 25% more balanced design. Just to give you a glimpse into our future, and that's my last slide. So now the method is applied on this floor plan that we have seen before, and two more, which I did not present. But we want to go for method valorization because it's giving actually promising outcomes. And what I mean here, we want to compare this method with as much practical designs as possible to see, to measure its robustness and see how promising it is, and to be integrated in practical design methods. Not only this, we want to implement the method into BIM software, namely Revit, as most Belgian companies use Revit, and Revit has the advantage of using their APIs, so the method can be easily integrated there. And that to increase the user friendliness of the method, so that you as a researcher can use it, or companies can use it for designing the systems. Finally, we want to do some further research to expand the method in two regards. First of all, going for simultaneous supply and extraction. Now, what we do is we design one system at a time, either the supply or the extraction. However, when putting the two optimized design together, we may deal with a case like this, having collisions. And here it's explained on a very simplified example, but when the case is bigger, you may deal with more collisions. So we look forward for tackling this issue in our future work. And another expansion is to apply the method for retrofitting or renovating application in case there's an existing system, ductwork system in the building, and the building is repurposed, to see how are we going to maximize the reuse of the existing system in an optimized manner. So thank you for your attention. I've added a couple of readings if you're interested in the method. And that's it for me. Thank you very much.